So my name is Mark Weber, and I'm honored to represent the MIT-IBM Watson AI Lab. We're a 10-year, $250 million initiative between MIT and IBM to do joint academic industry research together. I studied finance at MIT Sloan and did graduate research at the MIT Media Lab. I'm also a Notre Dame alum. Sounds like there's a lot of us, yeah. And now I'm on the IBM research side, right across the street from MIT. I wear a few hats at the lab. I lead our strategy and operations. I run our business program for member companies, and I do some applied research on AI and finance. So today, I have my research hat on, and I'm representing one of our 49 active projects, which is focused on accelerated and explainable graph deep learning for financial applications. Our MIT-IBM team is a really nice triangulation between the graph deep learning side, led by my colleague Jia Chen, the high-performance computing side, led by Professor Charles Leiserson at MIT, CSAIL, who wrote the Intro to Algorithms book that a lot of us have read, and then the applied side with my colleague, led by my colleague Toyo Suzumara and myself. I'm actually accompanied here today with my co-author on this paper, Giacomo Domeniconi. And this is a tutorial paper that we've written sharing some early experiments we've been doing on graph convolutional networks, looking at a new and interesting data set that is a labeled Bitcoin transaction data set, which I'll be telling you more about shortly. First, we'll talk about the unique challenge and opportunity of anti-money laundering specific to Bitcoin. We'll describe the elliptic data set, which is exciting, as I mentioned. And third, we'll look at the experiments and where the results are leading us next. So here's a primer on AML in 2019. As Catherine mentioned, hundreds of billions of dollars in money laundering fund drug cartels, human trafficking, terrorism, and political corruption. In an effort to stop this, our governments are enacting stricter and stricter regulations, which result in big fines for noncompliance, as Catherine mentioned. And unfortunately, this has a disproportionate negative impact on low-income people, immigrants, and refugees in a world where 1.7 billion people are still unbanked. This is because, as Catherine mentioned, the compliance bears high fixed costs for financial institutions, which they pass along to customers, and it also excludes people outright because so many low-value customers from high-risk countries are not worth the risk to the bank. Here's what this looks like for Danske Bank. Their market value completely collapsed after the money laundering scandal last year, which involved Estonia hub that is estimated to have been the hub for $200 billion in illicit money flows from Russia and Azerbaijan over the last several years. And both Danske, Deutsche Bank, and Swedbank have each lost many billions of dollars from this scandal, and it's still continuing to unfold. And that's just the most recent, really, in a number of major money laundering scandals that have hit. Here's how it looks like on the financial exclusion side. These are 2018 cash flows to low and middle income countries. And there's two things I want you to notice. One is, look how important remittances are compared to global aid. This is people sending money home. So this is a really important source of income for many people around the world. And the second thing I want you to notice is that 37 figure. That's $37 billion, represented by an average 7% transaction fee on remittances. And that's $37 billion that's not getting to low-income households. So this is a serious, that would be 25% of the current global aid figure, or 24% to be exact. That's a lot of money, and I think a tremendous social opportunity to focus on, as well as the financial opportunity. So here's an interesting question. Can Bitcoin help? When I was working at the Digital Currency Initiative at the MIT Media Lab, this was a major question. A common word, a common cause in the cryptocurrency community was that of financial inclusion. So if you look at cryptocurrency startups, you'll see dozens focused on remittances and championing the cause of financial inclusion. And many of them have been focused on lower transaction fees. But when Bitcoin's price skyrockets, and I'm using Bitcoin as kind of the front runner, but we can talk about any number of cryptocurrencies. When the price skyrockets, the transaction fee differential actually diminishes. So I would argue that it's actually the AML opportunity that makes cryptocurrencies like Bitcoin really interesting, and we'll talk about that. So here's this double-edged sword, AML-wise, for Bitcoin. On one hand, Bitcoin is pseudonymous. Criminals can obfuscate their identities and hide in plain sight. And many have used this feature to execute ransomware attacks or conduct activities in dark marketplaces. But Bitcoin is also public. And that open data enables forensic analysis and crowdsourcing that's not possible in the traditional financial system, where each financial institution is responsible for submitting suspicious activities reports. And it's really up to their own team to police their little piece of the system. So if we can tip the balance here, maybe we can use cryptocurrency as a boon for AML rather than as a threat. So next, let's talk about the Elliptic Data Set. One of the companies at the forefront of anti-money laundering in cryptocurrency is a London-based startup called Elliptic. They monitor suspicious activity in cryptocurrencies, label suspicious addresses, and perform advanced analytics to try to track bad actors throughout the public network. We reached out to Elliptic precisely because we were having such a hard time getting real-world transaction data, and synthetic data wasn't doing the job. And we were able to strike a nice research collaboration with them where they were able to bring data to the table. And I'm very happy to announce today, for the very first public announcement, is that Elliptic has donated a subset of their data to be available for the AI and AML communities to try to develop better methods. And so I'll describe that data set here. This is available on Kaggle. I've tweeted out the link just a few minutes ago from my account, Mark R. Weber. And to our knowledge, this data set is the world's largest labeled cryptocurrency data set publicly available. And it's actually possibly the largest cash transaction data set labeled that's publicly available. There's one bigger that's like credit card transactions for tracking fraud. But as far as cash goes, I'm not aware of one bigger than this. There are over 200,000 node Bitcoin transactions and over 230,000 directed edges or payment flows, which you heard Catherine mention is an important aspect of this, is how is money flowing through the network. 21% of those transactions have licit labels, meaning these are known exchanges, wallet providers, miners, etc. And 2% have illicit labels. These are known scams, malware, terrorist organization, ransomware, etc. So you can imagine if somebody executes a malware attack and they say, pay to this Bitcoin address, Elliptic says, okay, we know that is an illicit Bitcoin address, so we label it as such. Now, this is important for as we get to the experiments. There are 94 local features, example, time steps, in and out activity, transaction fees, and 72 one-hop aggregate features, denoted by LF and AF in the forthcoming slides. And these are things like max, min, standard deviation, correlation coefficients of the neighbor transactions. So these are going to be important when we look at method variations. And on to the experiments and discussion. So first, a primer on graph learning methods. Most deep learning to date has been on Euclidean structured data, audio, images, video. Deep learning on network structures is much more difficult, and it's lagged because the combinatorial complexity and nonlinearity issues involved in graphs creates prohibitively long training times for graphs of any meaningful size and density. But it's precisely the information hidden in that complexity that makes graph learning so interesting. So in the last 2 years, we've seen some big steps forward on scalability, and graph neural nets are now a very hot topic, including at this conference. Here we're looking specifically at graph convolutional networks, or GCNs. With GCNs, we begin with certain attributes to describe the nodes and edges. Then we perform linear transformations of these attributes and aggregate that information by probing the neighborhood of each node. Then we repeat this process over and over again to arrive at an embedding vector for each graph node. And we call this node embedding. And this is going to be important, again, when we look at our experimental results. So let me explain that in different terms. Node embedding is kind of like this existential question, who am I? It's a question of infinite complexity, but we need a vector of finite length. Moreover, we want to solicit input from my neighbors. It's not just about who I say that I am, it's about who others say that I am, right? But we don't want to get input from all of my neighbors because that would take too long. So we have to bound the model to balance this trade-off between accuracy and efficiency to create training times that we can iterate through. So turning back to the elliptic data set, we're going to evaluate variations of GCN against some benchmark methods. The task is a binary classification, and the two classes are imbalanced. This is important. For AML, the illicit class is more important, right? So we trained our GCN using a weighted cross-entropy loss to provide higher importance to the illicit samples. And for benchmark methods, we're going to look at logistic regression, multilayer perceptron, and random forest, and we create variations of these using mixtures of the local features, LF, the one-hop aggregate features, AF, and the node embeddings, NE, from GCN. And the results are very interesting. First, the overall best model, shown in the red highlight, is a graph-aware random forest GCN hybrid. What that means is we're using the aggregate feature information provided by Elliptic in the original data set, plus the node embeddings from GCN. That's the process I just described. Second, I want to draw your attention to this precision column and the blue highlight. The precision is the probability of correct detection of positive values, meaning illicit values. This is especially important in AML because we have a cost asymmetry between false positives and false negatives. And so we need to make sure we're not letting any bad guys through. And if you look at the blue highlight, we see that the GCN node embeddings provide an 8% increase in precision to a graph-agnostic random forest. And this is really quite big because we see that bump or similar bumps in each of the different methods evaluated. And this captures that GCN is finding something deeper than what the handcrafted relational information provided is coming up with. Now here are those same results over the first 42 time steps. But watch what happens here. All the models suddenly collapse. Can anyone guess what happened?
The value of Bitcoin went down.
It wasn't the value of Bitcoin, although it may have gone down as a result of what happened.
The theft was
Actually, it might have gone up, actually. A dark marketplace was shut down by law enforcement. And all of a sudden, the nature of illicit transactions fundamentally changed. The system got shocked, and all the models failed. This brings to light an important challenge for AI and finance, not just for AML, and that's the robustness of our prediction models relative to sudden changes in the system. And as my former professor Andrew Lowe explains in his book, Adaptive Markets, the financial system is an adaptive biological system. And so we need to have methods that deal with that type of dynamism. And here's one we've been working on. Well, this is called EvolveGCN. And did it go? Yeah. One method we've called is EvolveGCN. Now, notice the two EvolveGCN methods seem to recover a little more quickly, back up to reasonable F1 scores. And here's how it works very, very quickly. EvolveGCN computes a separate GCN model for each time step. And these GCNs are then connected through recurrent neural network to capture the system dynamics. So the GCN model for a future time step is evolved from those in the past. And the better the model is able to capture the core system dynamics in play, which are also evolving, the further into the horizon the model can project, right? So this is in progress, but here are some of our early results. And lastly, with the last minute, I just want to touch very briefly on explainability, which is, of course, a fundamental requirement of any system that operates in AML. As an aside, I was getting my shoes shined in the airport on the way here, and I met the gentleman shining my shoes was a retired banker who worked in AML, and described it was pretty crazy. He described a situation in the 2000s when they realized that there was some sketchy business activity with one of these accounts, but the account had a relation to a family member of one of their big reputed clients. And so they tracked this account for 2 years, but they couldn't shut it down because they couldn't explain exactly why they needed to shut it down, and there was no clear wrongdoing. And unfortunately, it turned out that after the 2005 London terrorist bombings, the financing was tracked back to some of those accounts. And they ended up getting fined, and more importantly, they were distraught that, gosh, we saw this thing and we didn't stop it. But for him, it came down to the fact that they couldn't explain and protect themselves from a lawsuit why something was suspicious enough to shut down. This unfortunately is not something we have solved, but we have kind of gone through some visualization tools that might help with regard to looking at these massive graphs and the anomalies in them and trying to unpack some of that complexity. So here quickly is a UMAP projection of the raw feature vectors that we start with. Here then is a projection of GCN layer activations. And lastly, we combine these, or we make these accessible through a simple prototype of a tool we call chronograph, which allows us to navigate through the 49 time steps in the elliptic data set specifically and try to track the model performance over time. So in summary, we've motivated AML not only as a priority for financial institutions, but also for society. We've described the elliptic data set, which is the largest of its kind publicly available. And we hope that this will galvanize researchers into action on this important challenge. We've shared our experimental results and the contribution of GCN, which is very interesting and continuing to unfold. We've observed the challenge of system dynamism and touched upon visual tools. And lastly, for you financial institutions in the room, or people who have data, we really need to evaluate these methods on traditional data. One of the reasons, even though we work for IBM, which has many financial clients, we haven't been able to access any data is because IBM is extremely careful with client data, so we haven't even been able to access it. But perhaps through one of you, we could strike a collaboration and develop these methods on real-world data so we can address these problems. Here's my information if you'd like to find me. Thank you for your time, and thank you, Sentil, and the other organizers of this great workshop.